Okay, hello everyone. This month we actually celebrate the fifth year anniversary of the Alma seminar, which is really great. And well, obviously to mark that occasion, there's no better speaker than David Salinas, who was the very first speaker of the seminar here 5 years ago. And yeah, David is back then he was still a research scientist at Amazon. Then he went to become a research scientist in Freiburg, and now he's actually since a couple of weeks group leader at the Alice Institute in Tübingen working on OpenULM. And yeah, with that, thanks a lot, David, for joining us, and stage is yours.
Yeah, thanks a lot for the introduction. And it's a lot of memories these 5 years. So yeah, that's it's a funny thing. So this paper is about tuning LLM judges. So it's a joint work with Omar Swelam and Frank Hutter. So and I guess it's the general theme is LLM evaluation. So I'll just briefly introduce how LLM are evaluated just to give some context and then describe kind of the methods that we propose for LLM judges. But so, yeah, or maybe do you see the window with everyone? Like my screen is fine, right? You just see the slides. Okay, that's good. Yeah, thanks. So, yeah, I mean, LM evaluation, it's a general problem. Because evaluating a generative model is hard, right? So that's I mean, here, for instance, those are all kind of questions you could ask an LLM, and if you ask it to compare and contrast renewable energies and ask two options. One may be better, but it's probably hard to exactly say which one is better, right? So that we often don't have really a ground truth. And given this, and I will describe some kind of methodology to evaluate LLMs, but typically it's important, like from the start, to realize that they are all going to trade off one thing. So maybe they spend a bit more compute, they are more accurate, they are more expensive, or they are more biased, but they make one of those trade-off. And so in machine learning, I guess we often have this how to say, this mindset that, for instance, all the models that we do I mean, are kind of maybe partly right, partly wrong. Some are useful for evaluation. I want to highlight that it is the same. So we don't have a perfect set of evaluation, and we will never have. Sorry. Right. So with that, let me introduce the main families of method to evaluate LLMs. So the one that you probably know or that you could imagine is like you could just ask a bunch of random questions to an LLM. For instance, I don't know, on math, history, and probe the general knowledge. So you would have the answer. So you have the ground truth in this case, and so you can evaluate exactly how good a model is for like, for instance, abstract algebra, or sorry, linear algebra, and this is one example for MMLU. There are a lot of other examples like that. So that's a very common way to evaluate. Of course, it only evaluates in a static fashion, so that's it doesn't how say evaluate how fluent a model is, if it's I don't know, if it speaks in a nice way, if it doesn't insult you, or like a strong bias and so on. Now, just jumping to the other generative part. So what about chat capabilities? So there you would need something more dynamic because, for instance, if you ask for like, I don't know, opinion about renewable energy, I mean, this is going to be subjective in a sense. And so there are like multiple ways to do that. One standard is to use human annotation, and Chatbot Arena in particular is quite popular. It uses code annotation, and I just show quickly how it works. Right, I mean, maybe I'll do it now. Um, okay. I mean, I don't know. I assume most likely everyone has have heard of it, but in case you have not, I mean, you can browse Chatbot Arena on Google, and you will end up to a website like that, and you can ask the question. For for instance, what is the best hyperparameter optimization library, and so you'll get two answers, and well, okay. I guess the first model just failed, so that's a bit. But you will see the model output of the first model and the second model, and then you will decide between the two, right? So for those, yeah, and here, for instance, this model mentioned optunar, retune, hyperopt, blah blah blah. It doesn't mention SignTune, which is a library that we developed, so that's kind of funny. I guess we could ask. Well, anyway, and yeah, you will decide which one is better. And so here it's clearly model B, but of course there will be cases which are kind of harder and to annotate. And so all those votes are collected, like 3 million votes that has been collected so far by Chatbot Arena, which is not LM Arena, I guess. And then you have some ranking for every model. Right. Okay. And so that's the new UI. My slide is based on the old UI, but doesn't matter. And so at the time I did this slide, that was the ranking. So Grok was like top 1. The best open weight model was like top 6. If you are looking for the best model with a post-training recipe, so where you have a code to go from the pre-train to the instruction tune model, you go down as 46 in the ranking. And if you want something that's kind of fully open, you will go down to rank 153, which I think highlights the gap between different kind of shade of openness in the LLM models that we have today. I mean, so this slide is from 1 or 2 months ago, but yeah, you have similar ranking today. So okay, so that's type evaluation is great from human feedback. I mean, it's just let's just say that you can query IID people. That's kind of like, you could say, kind of a golden standard. Like one issue is that it's going to be very expensive. So there are like some work that estimated how much how much it will cost you if you were to pay for like human salary and so on. And the estimate is maybe you need to spend like $3 or $4K dollars to evaluate one model. So if you want to do your model development, if you want to do hyperparameter optimization, that's I mean, I guess if you're a big company, maybe that's fine. I mean, that's certainly fine. But if you're not, then yeah, you can't do this way. So instead, LLM as a judge has become quite popular. And so the idea is that instead of asking humans, you ask an LLM to tell which output is better. So for instance, there will be some ambiguous kind of set of 2 completion. And rather than asking where instead of asking a human, you ask an LLM, and I mean, you prompt it, please say which model is better, and it will tell you, for instance, model 1. And so the big benefit is like, obviously it is cheaper than human annotation, like much cheaper, and it can evaluate open-ended text. There is a benefit that I did not put it here, which is also very valuable. It's purely how to say synchronous, in a sense like you want to evaluate your model, you just run through your LLM as a judge, and once everything is done, like in a couple of minutes, you have your results. If you use kind of human annotation, you obviously have to wait a few days, and that makes kind of the model development also harder and longer. There are a few cons, just listing a few. I mean, one is like the LLM judge, they can be biased in many intricate ways. I mean, they how to say, they mimic the human judgment, but they just mimic it. And sometimes they have some failure mode. For instance, they tend to prefer longer sequences. They tend to kind of overemphasize if like the position of the model. So if you swap this model 1, model 2 answer, and you ask LLM as a judge, it may give you something different. So yeah, it has those issues. So some can be addressed. I think a big problem is that all those LLM as a judge paper, 99% they rely on GPT-4 or like a closed model, and that's bad because I guess for two reasons. So if you use it for leaderboard, I mean, the leaderboard may disappear if like GPT-4 deprecates their API, for instance, of a given model. Also, also, like it has been shown that actually GPT-4 tend to prefer its output as a judge. So that's so we don't want to how to say GPT-4 is strong enough as it is. Maybe we don't want to reinforce it, but in this way. Right. And so LLM as a judge, as I mentioned, can be used for model selection. It can be used to build leaderboards. For instance, hyperparameters is a famous leaderboard based on LLM as a judge. And yeah. So our goal in this work is to provide high accuracy, low-cost LLM judges with open models. Um, um, Maybe I think I'm kind of I forgot if I've said this, so sorry. Right. So I said here that LLM as a judge are kind of cheaper than human annotation. Previous work, the LLM judges evaluation will cost around $20 per model, so it's much cheaper, but it's not like I don't know, super cheap either. So you may want to have an open model and something that is cheaper. Okay, cool. So I guess we'll jump right into it. So yeah, we are just going to apply AutoML to LLM judge configurations. There's just some subtlety on how to make it work, which I'm going to explain. I mean, one thing is how do you parameterize your search space? So it's always a question. AutoML. In this case, we do something very simple. We just parameterize a prompt like this. So we have different output formats. So for instance, how the judge should kind of give its preference. So here it gives a number between 0 and 10 for score A and B. I mean, for the output of assistant A and B, but we could phrase it in different ways. We have several booleans, so like whether the LLM as a judge provided answers. So like some people think that, for instance, asking the LLM as a judge to provide answer is provoke something like a chain of thought, and so that then it's going to be better, or other explanation. And so all of those things we just have a boolean. So to whether we do it or not, we have a boolean whether we use JSON formatting or just like a raw text. So we also have some inference hyperparameters. So you can always choose the LLM judge that you use or any model that is available. We just use open weights models for the reasons that I mentioned. So we try 7 variance and 4 temperature. So, and the last thing that we have is a Boolean. So whether this thing I mentioned, this problem where the LLM as a judge may have a different kind of output if you swap the assistant completion, you can just do the two possibility and average them out, and then you know it's not order dependent. Right. So overall, we have, I mean, yeah, like we have 80 prompts, so 5 choice for the formulation and 4 booleans. And so that gives 4,480 judges because we have also like all the temperature and LLM models. So now, okay, we could evaluate all of those judges, but like if we just brute force it, so to say, it would cost around $2 million. So like I will explain why this cost would be so high, but like we just want to do something, I don't know, not too damned on how we evaluate those judges. Right. I didn't say when I started, by the way, but if you want to interrupt me at any time, yeah, you are welcome to do so. Right. So Okay, another method. So we have this search space. What we are going to do is that we are going to apply multi-objective optimization. So we optimize the accuracy and the cost of judges so that we find good set of trade-off for LLM judges that are either kind of expensive and accurate or like kind of or trade-off like a bit the accuracy for the cost. And just want to compare to what was done before. So before, configurations were manually selected and evaluated. That's one thing. And also every paper will basically introduce its own judge and will change, I don't know, 3 different things. So for instance, it would change, like the paper would change I don't know, the LLM model, like the prompt, the output format, and then you don't really know which one. I mean, why this thing is better, right? So that was maybe an issue. So for instance, to give an idea, this is from Alpaca Eval, from their GitHub, they tried different judges. And here you see the price per 1,000 example. I mean, it's basically multi-objective optimization in a sense. And they say, hey, I know if you do chain of thought, it improves correlation, but increases cost. And if you use an open model, like it's worse, but it improves the cost. And this is something that we want to tune. So okay, and I said this $2 million like would be the cost to evaluate all judges. So why? Because evaluating a single judge in this setup where you evaluate, I need to move this window, the Spearman correlation. Evaluating a single judge configuration like this one, for instance, it costs like around $400. Why is it so expensive? Because you need to annotate a list of prompts. So like for instance, in Alpaca Eval, there is 805, I think. So you need to evaluate 805 prompt or instructions and then as many model as you need to compute the Spearman correlation. So typically 20 or 30 models. So you need to evaluate for all those models. You need to run your judge through a product of instruction and model, and that's why it's kind of quite expensive. And yeah, so what we do is that we just identify a cheaper metric, and then we use, I mean, an AutoML approach to just do better than just random search. Okay, so the better metrics. So as I mentioned, option 1 is compute Spearman correlation. For that, you evaluate a list of LLMs. So let's say you have 20 models. Then you call LLM as a judge on a list of annotation. And then you compute the win rates. And then you compute the Spearman correlation with what's the ranking that was obtained in Chatbot Arena. That's option 1. Option 2, I mean, it's much simpler, but just human agreement. So you pick a list of battles. So a list of like triplets where you have an instruction, the output of model 1, the output of model 2, and the preference of the human. And then you just call them as a judge on this, and you compare with the human label. So that's pretty straightforward. So both options are kind of technically, I guess, kind of valid. So they do different things. So one question is like, okay, but how good are they given an amount of like, I don't know, kind of annotation that you spend? How good are they to kind of distinguish a signal from the noise? So what we did here is that we went through, we use Alpaca Eval, Hard, and the union of both instructions, and we run an LLM as a judge with the same prompt, and we just increase the model size of the LLM judge, right? So that's the only thing that we change. So we do expect the LLM as a judge with 72B parameters to be better, right? And we kind of see that. I mean, that's higher is better. So that's like, for instance, this model is worse than this one. So we see that. And we see that the confidence interval gets slightly kind of, how to say, slightly smaller when we increase the number of instructions. But for instance, with Alpaca Eval, actually, it messes up the order between the 32B and the 72B kind of judge. And here, like the confidence interval are completely overlapped. So that's, it just maybe shows kind of the limits, right? Because it can distinguish multi-fidelity and 72B. So in contrast, we look at human agreements and we increase the number of instructions. And there, I mean, we see that, I mean, the mean, at least performance of the 72B model is always better. So that's good. It managed to distinguish the performance of the different judges. I mean, this metric. And if you will zoom out, you will see that the confidence interval actually with this number of instructions don't overlap. They overlap in all cases, even when you take the union of instruction over there. So this seems like a much better metric. I don't know. And we look at our stuff like measures the signal to noise ratio, and it's kind of a percentage basically. And like the percentage is just much better for the human agreement. So that's basically, if you want to tune judges, there is no point. I mean, yeah, you just shouldn't do Spearman correlation, which I mean, makes sense, but that's just one way to kind of confirm it. Okay, so that's a definition of the signal to noise ratio, coefficient of variation. But yeah, that's just what I said. So, okay, so we identify this metric. It's good, like it's cheaper. It's the same number of annotation. We get something that's much cheaper, but we still, I mean, it will still be expensive to do a brute force over all 4,000 judges. So what we do is, so we have two objectives, and so we just apply multi-fidelity, multi-objective to the rescue. So we evaluate 4,000 configuration. We pick the best 400, then we pick the top. Sorry, I got it wrong. So we evaluate the all judge configuration on 400 instructions. Then we pick the top, and we evaluate those judge configuration with more instructions, and then we pick the top 400, and we evaluate it with even more instruction. And a big thing is how do you do the top configuration when you have multiple objectives? So we use non-dominated sort to determine the top configuration. So that looks like this. So just let's say if you were to rank, I mean, if you want to rank this point cloud, you will, the non-dominated sort will first compute the Pareto front and assign top rank here, and then it will assign top rank there to the remaining point, and so on and so forth. And how to say, like, you need to break the ties between when you computed the Pareto front, is this one the first, or is this one the first? This is done with a heuristic. Yeah. And so, for instance, those are all the judge configuration that we evaluated to illustrate the algorithm, so to say. So we apply this non-dominated sort gives kind of this rank. So in this rank, like yellow is higher, so those judges are selected first. And then we do another round, and those are the 400 that remains at the last stage, right? Yeah, interesting enough, like Bilal is here, so that he's a co-author in a paper that proposed to do this. So that's, yeah, a long time. Yeah, and so, okay. So now we've yeah, I mentioned how tune should yeah, sorry. I want to show how, I mean, empirically, how does it work? So does it compare with like previous LM judges, like to kind of close weight models and so on? So we have three benchmarks. So the first is LM-based test set. So I didn't say on what we compute the human agreement. We compute it on the LM-based data set. So we keep a set of instruction for validation and to run our algorithm, and then we pick the best, and we report it on the test set, some instruction that have not been seen there. And here you can see, and okay, so we have three judges, like small, medium, large. So we do have a continuous trade-off. So, but we I don't know, we thought it would be better. It's more standard, I guess, in the community to have like three model sizes, because for hardware kind of deployment reason and so on. Right. So we pick a small, like I think it's like lower than 10B, between 10B and 70B is a medium, and large is larger than 70B. So for all these categories, we pick something from what our algorithm return, and we compare the human agreements with multiple baselines. So random is 33% because the human choice is just A, B, or tie. So length is it's just picking the longest answer. So, and this is actually much better than human agreement because sorry, it's much better than random. It's actually a much better human agreement than random, which is interesting. Just like human actually tend to prefer longer answer. That's just the case. And you can see some baselines that actually don't outperform this simple thing, this simple length baseline. Right. And so that the model that we propose, so that I guess the largest which would be the fair comparison of having a hand, which runs a GPT-4 model. The confidence interval overlap are in a hand, but the cost is much lower. We also ran on other kind of benchmark judged dataset. So one is from Panda-LM. So in this case, it is Panda-LM is a LLM as a judge approach where you fine tune on some data, right? And so they fine tune on a data set and report the performance on the test set. So arguably the fine tuning kind of makes your life easier because you can kind of see the distribution quite a bit more. But even in this setup, we beat all the fine-tuned judges, and we still outperform GPT-4 in this setup. And we also compare in Arena Harm. So the judge proposed in Arena Harm. Yeah, I mean, we have like, I guess our confidence interval again overlap with Arena Harm, but we have much better cost. I mean, I could, yeah, I mean, maybe I won't. Okay, like so something I didn't say, but it's good in case you are interested in LLM as a judge. So it may be evaluation. So something that happened before also is that like the performance was reported on the same set of model used for the model selection of your judge. So for instance, Arena Hard, in this case, I think you are considering 20 models. And so all the model selection was done optimizing the Spearman correlation on those 20 models. But it's clear in hyperparameter optimization that it's kind of not a good idea if you want to if you apply your hyperparameter optimization on something, you should do that on the validation set. If you do with the same metric, you obviously risk overfitting, and those scores are, I would say, very likely overfitted for that reason. Okay, so that's good, but then yeah, from the data that we have, I think it's good to have like open models, but it's just interesting to see what works well, what doesn't. So as I mentioned, that most comparison before was kind of apple to orange, or everything was changed at once, so you can't really know. But here, because yeah, we evaluate everything and so on, we can actually see, I mean, which hyperparameters are important and so on. I mean, you could do it in several ways with, like, for instance, fitting a model and looking at what hyperparameter is important. So in our case, we just did a survival analysis. So we look at among the top judges that are selected, what is the proportion, the top 100 for every hyperparameter. And we split this analysis for small LLM judge models, so like with lower than 10 billion parameters and more than 10 billion parameters. And so here, well, obviously, when we only consider 10B parameters, we only have 10B kind of models remaining, and they have like roughly equally selected. Here, it's clear that there is an advantage for Lemma 370B, which appear to be the best model for the kind of for judge in this setup. For the all right, for the temperature, roughly all temperature are kind of, I don't know, are fine. It's just like you don't want to have very high temperature. That seems to be the thing that hurts performance, unlike creative writing, for instance, which probably makes sense. Here we see that's, I think, quite interesting. So the format is actually super important. So, and this pair format, and that's actually this example I was showing in the prompt, like where you have score A and score B, this seems to be just a very good kind of output format. And right, and so asking performance or explanation generally also, like, you can look at the mean, but generally it makes the result like slightly worse on overall, but it doesn't it's how to say, it's different for like small and large judges. Like, for instance, providing an example, it helps when you have a large model, and it hurts when you have a small model, which kind of makes sense, right? So it's just you're just putting more things to in the prompt, and the LM do not have enough capacity, so just confuse it. And look at other things. Does the JSON format helps or not? And okay, so I guess it can be used for practical recommendation for folks. We also study the prompt generalization, how much a prompt performance generalizes across models. So let's say you have one prompt that works really well for one model. Is it going to work well for another set of models? So that's a very natural question. So for that, we study the correlation for every model between the 80 prompts that are performance of the 80 prompts that are available, and we compute this correlation matrix, which is kind of clustered. And what you can see is that if you pick model with similar size, for instance, here 9B, 8B, 7B, it's usually pretty high correlation. And of course, if you look at the correlation between 7B and larger model size and kind of differ, there's also, like the previous thing I was showing, that for larger capacity of model, for instance, providing an example may work, whereas it doesn't with low capacity. So that kind of confirmed that in a sense. Okay, so conclusion on this part of the talk, the LLM judges, they can be tuned at a reasonable cost. I hope I convince you of this. If you tune the hyperparameter, you can match the performance of previous approaches just with open weight, which is nice. Like the cost, also, like, you can do that at a much lower cost. And yeah, and only with open weight model. So in case you are going to ICML, yeah, please say hi. That I will present this paper there. Just okay. So some next steps in future work. First, okay, so the code is released, so all the data is available, all the judge annotation and so on. So I hope okay, one step is clearly the algorithm that we do for searching judge is still pretty I don't know, straightforward. You can probably do better with something model based. You could do ensemble of judges. Those are all things that can be done for free with this data. So if you are interested, I encourage you to take a look. I think a potential next step for this work is to optimize the instruction tuning pipeline. So instruction tuning pipelines are quite secretive, and there are a lot of hyperparameters. For instance, do you use PPO, DPO, what learning rate, what regularization to the initial model, so on and so on. And one thing that I think was taken, why AutoML has not been applied there, like just some kind of good HPO methods, is that just the evaluation were too expensive. I hope now that maybe that helps to makes it a bit more accessible, and maybe that will be a possibility. And the last thing is, I guess, next step future work is to use those open judge configuration to evaluate model trained by OpenULLM. And that's maybe I can talk about this. So that to motivate this, I just want to make, I don't know, a case for openness, so to say. Maybe it's an easier case of all, but just want to list some, how to say, projects. Like I guess that's the largest project that I could find, recent projects done by humans in a sense. So the LHC, it cost 5 billions and it involved like 23 countries. So there is a plan for a much better one. I have no idea how much it will cost, but that would be probably ridiculous. There's a Hubble telescope, it costs 16 billions, it involves 11 countries. The ITER fusion prototype costs like 45 billions and involves like 35 countries. And the most expensive of all that I found was an international space station. Also, not state space. It's an international space station. Yeah, sorry. Use And it costs 100 billion. So it's pretty big and involves like 16 countries. And one example of like a very, I guess, sad project that technically I checked. I think it involved like UK and other countries, not just US, but I mean it was pretty much just the US. But it's a Manhattan project. It was pretty expensive, and the outcome was not so great. So you can see where I'm coming from. So like, and then we have LLMs. So right now it's really an arm race. So we have one world where we have n actors. They all develop their LLM secretly, mostly. Sometimes they share a bit, but also the time maybe they don't. And they compete, for instance, in chatbot arena. So that's that. Um, and and the as a, I guess, annoying thing here is that because of scanning compute efficiency, so it's a bit sense, so it's much easier to scale compute. The cost is really rising up because I mean it's easier, so to say, to just add more GPU compared to adding more finer prior or language because we don't know how to do that. And so we have hardware improvements, so nice. So like it's not exactly Molo, but seeing exponential improvement. We also have exponential improvements with algorithmic progress. But I mean, whenever, like, I mean, every year, let's say everything becomes 8 times cheaper, we still rise the price exponentially of training models, as you can see here, because economic benefits are huge, or are supposed to be. I don't know. And of course there is it's not like everything is not like that. So there is an alternate world, so to say, where we share the open weights. So some company do share open weights, some do that more than others. And those models they are really important. So they without them we would not have this startup ecosystem and all this amazing research. They're also like fully open models. There's a big difference between the two. So in performance, but also in usability for, I guess, a community. And so, and maybe at this point, you're thinking, okay, but that's nice, but it's how to say, yeah, it's a for-profit thing. We like people need to make money; they can't collaborate. So I just want to give one big counter-example. So AI, it rely on high-performing GPU, and this rely on the biggest industrial or one of the biggest industrial collaboration in history. So yeah, maybe you can think about it like a few seconds. Actually, let me ask: does anyone know which technology I'm referring to here? I see the chat message. What wafer making? Yes, exactly. That's I mean, and in particular, I'm referring to like a extreme ultraviolet. I mean EUV lithography, which is really the core technology that powers AI. So that's a EUV machine. So it costs about 400 millions. And okay, so sadly you can't buy it because it's all sold out. And that's really what is printing, so to say, all the GPU, because it prints at a much finer resolution than the previous technology. And so this technology is really a big deal. So it costed like between 14 and 21 billions on the estimate I could find to build this machine, like to do the research that, and it really involved like many countries and decades of research. So it involved like Philips, ASML, Intel, and so on and so forth. So like and but right now there is a single company that can build those machines, so it's ASML. There is no equivalent like, and that's when you think about it, it's something kind of crazy. That's really I would say the best. Well, I don't know, most strategic companies in EU, I guess you could say, for like this sort of technology right now. In case you're interested there, I recommend reading those two books, which are really nice. See message in the chat. Yeah, and yeah, exactly. And that's I mean, one day I wish I would see that campus is supposed to be quite big, and it's a very discrete company in a sense, but like it's such a big impact. So that's very interesting. Company now, which brings me to Open LLM. So it's an effort to build multilingual LLM from scratch by 2028. It started in February 2025. The goal is to have models that are fully open, weights code and data, and that provides great performance for all EU languages. So there is like about 40 million euro funding and lots of GPU hours on top of this. So yeah, the project only started in February. We are planning though to release some kind of 2B model with SOTA performance among free open models. So here I'm showing just one kind of scaling analysis where we show the average downstream performance for a bunch of benchmarks on like for like I said, several baselines, and that's the model that we trained so far. And so basically it's like vanilla transformer trained with different data sets, but like with a really strong effort to have like very kind of I'll say performant pipelines, so that we can then train larger models. We are currently hiring 9 researcher engineers. So if you're interested, yeah, please ping us. If you are also, we are also looking for internships. Also, if you're interested in collaboration, there is a lot to be done and way to match that we can actually do. So, and yeah, and like we want to see, we are going to scale up the compute and where we stand with like kind of larger models. So ideally, we'll be up there. I don't know. Let's see. But in any case, if you're interested, ping me or Aaron. And yeah, and like I guess that would be an audience for like AutoML. There are lots of areas for AutoML in this kind of line of work, like for retraining, post-training, evaluation, everything. So yeah, and we're just scratching the surface. And yeah, that's the end of my talk. So I'm happy to take any questions. Yeah.